we will talk about extrema problems on an interval in this lesson. Let's first define extrema and relative extrema of a function on an interval. Well, speaking of extrema, when there's no adjective there, extrema also means absolute extrema. Extreme means extreme values that includes the largest and the lowest extreme values. So now let's read through the definition. Let f be defined on an interval I containing c. Then this guy, f of c, is an absolute maximum, and we sometimes call it global maximum, when the following is true. So what is true? F of c is greater than or equal to f of x for all x in this interval I. Basically, that means this f of c is the largest value of f for all x in this interval I. So that's what we call it absolute maximum. Now let's quickly skim through, look at this graph. Okay, we have a graph that's defined from -1 to 4, and there were some special values marked. So in this case, we can see that this point A, the y value is 37. It is largest on this interval. It is greater than or equal to any other y values in this interval. So in this case, this point A achieves its absolute maximum at x value -1, and the absolute maximum value is 37. Now the next is the absolute minimum, or we also call it global minimum. On I at C, if f of c is less than or equal to f of x for all x in I, you can see that when this f of c is smallest value, then we call it absolute minimum. And again, refer back to this graph, we can see that this point, when x is 3, the y value is -27. This is the lowest value that of the function on this interval. So in this case, the absolute minimum value will be -27, occurring at x equals 3. Next term is relative maximum, or called local maximum. If f of c is greater than or equal to f of x for all x nearby c, it's not for all x in this interval, it's just for all x nearby c. So this is a little vague definition. Basically, a little more rigorous way to say it is in some open interval that contains c. So it has to be open interval containing c. Now let's go back to this graph, and then we can see that the point C achieves a local maximum at x equals 1. Why? Let's check these requirements, right? So in other words, f of 1, which is 5, right? So f of 1, which is 5. And we can find that there's an open interval that contains x equals 1. And then all the y values here, this f of 1 is greater than all the other y values in this interval, right? So in other words, f of 1 is greater than or equal to f of x for all x nearby 1. So therefore, this point is a relative maximum. Now, some of you may say, what about the endpoint A? Well, we don't use endpoint for relative maximum because we have to have some open interval that contains C. So because here the function is defined only from -1 and to the right, there's no such open interval that contains -1 because function is not defined for y values less than -1, right? So therefore, this is not considered as relative maximum for that reason. Similarly, relative minimum, or called local minimum, if the following happens: f of c less than or equal to f of x for all x near c, and this has to be open interval again. And refer back to this graph, we can see that point D right there, and then we can see that we can find a open interval that contains 3, so that all the values on this open interval, all the y values on this open interval is, we can see that like this is true. This f of 3 is less than or equal to the values nearby, right? So therefore, there's a local minimum there. Again, a quick note, local extreme values, including local maximum, local minimum, they are not at endpoints. Why? Because of the open interval restriction there. So you don't have open interval that contains an endpoint. Now let's do some exercises. Let's look at a few graphs, and for each one of those, let's identify the locations or the points, x values at which local and absolute extreme values occur. And then if needed, refer back to the definition. And I will encourage you to pause the video and give a try first. Let's look at the first graph. We have this graph defined by y is h of x and defined from a to b. In between there is c1, c2 here. The local max is it occurs at x equals c1, right? Because right there the y values are the y value at c1 is greater than or equal to the values nearby, so that's where the local max occurs. Local minimum, similarly, it occurs at c2 because this value is smaller than or equal to the y values nearby. And absolute max, which is the largest value in this interval, including the endpoints. So in this case, the endpoints are well defined. At function is defined at a and at b, and we see that this value is greater than or equal to all the y values in this interval. So absolute maximum occurs at x equals b, and the absolute minimum occurs at c2 because the y value at c2 is the smallest in this interval. Next, let's look at the part B. Part B, this function is defined, well defined at endpoint A, but it's not defined at endpoint B, right? Now let's again identify where the local max, local min, absolute max, absolute min occur. So for local max, we see that right there, this at C, the y value is greater than or equal to the y values nearby. So this is where the local max occurs. For local min, I'm not able to find any x value so that the y value at the x value is smaller, less than or equal to the values nearby. So I don't see any, right? So therefore, it actually does not exist. There's none, basically. There's none. It doesn't have any local min. And absolute max, and you are looking at the largest y value, which occurs right there, which is occurring at C. And absolute minimum value, and then we are gonna look at the right endpoint. However, this right endpoint is not defined. Therefore, there's no such absolute minimum. So in this case, absolute minimum, there's none. In the graph C, the local max, we have to look at the points inside the interval. We don't see any y value that is larger than the values nearby, right? So therefore, there's none in this C. There's no local max. Now the local minimum, we can see that at C, the y value is less than the y values nearby. So therefore, local minimum occurs at C. And absolute maximum, you are looking for the largest y value, so which is occurring at this endpoint A. So this is the absolute maximum, so it occurs at A. And absolute minimum, you're looking for the smallest value in this interval, which is occurring at C. Now let's move on to part D. Let's look at the local max. So we're going to look at the x value inside the interval. And unfortunately, at C, there's no such largest y value that's larger than or equal to the y values nearby, right? Because here, when x is equal to C, the y value is actually defined right there. It's not up there. So therefore, there's no such local maximum, so there's none. And the local minimum, again, I don't see any y value that's less than or equal to the y values nearby, so there's also none again. And absolute maximum, we are looking for the largest y value because this is an open circle right there. There's no largest y value, so we don't have any again. And the absolute minimum, and we're looking for the smallest y value, which occurs at the endpoint A, right? So therefore, it occurs at A. Next, let's look at E. Let me zoom in a little. Here, the first one is the local max. The local max, we are going to look at the interior point and where the y value is larger than or equal to the y values nearby. We can see this is a local max and this is another local max, right? So therefore we have two local maximum values. One occurs at P, one occurs at Q, not Q, but R. So one is P, one is R. Local minimum, we look for the y values less than or equal to the other y values nearby. So we can see that this is a local minimum and this is another local minimum. Therefore, we see that they occur at Q and also S. Absolute minimum, we have to look for the y value which is the largest. It seems to me this y value is the largest because it's taller than other y values, right? So therefore, I'm going to call that as the absolute maximum occurs at P. And the absolute minimum, this is the smallest y value that we see. It occurs at A. Now, last one, local maximum, we see that occurs at P, occurs at R, at those 2 points, P and R. What a coincidence here, right? And then local minimum, we see that Q, and we don't see this as a local minimum because left side is greater than this value, right side is less than this value, right? So therefore S is none. And the local minimum occurs at Q in this case. Absolute maximum, the largest y value occurs at P. And the absolute minimum, the smallest y value occurs at B. So therefore, P and B for absolute max and absolute min with respectively. All right, so hopefully you feel comfortable with those terms after going through these graphs. Next, we're going to introduce several couple theorems. The first one is so-called extreme value theorem, and it says if f is continuous on a closed interval a and b, then f has both an absolute maximum and absolute minimum on this closed interval. So this theorem guarantees when these conditions are met, then we must have absolute max and absolute min on this interval. And then let's refer back to the graph we just looked at, and which of the functions in this problem number 1 meets the conditions of extreme value theorem. So I want you to pay a little attention on the conditions. So the conditions, there are several conditions. One is continuous, right? And second, a closed interval. So let's see. The first one, this is continuous and closed interval, so it definitely meets the condition. The second one, this is not a closed interval. The right endpoint is open, so therefore this is not a closed interval. It is continuous, however. Now the next one, there's a little continuity here, so therefore f is actually not continuous on this closed interval, even though the domain is from A to B, including the A. However, this is not continuous, so therefore this graph C doesn't meet these two requirements. And D is definitely not, right, because it's not continuous. And D is continuous, and both endpoints are defined, so this function meets both requirements, and same as F. So therefore we can see that A, E, F, they all meet the requirements of this extreme value theorem. And observe the graph in problem number 1. For each graph, what is the slope of the tangent line at local minimum or maximum when tangent line exists? We can see that we are going to look at the local maximum and local minimum. So at C1, where the local max occurs, what's the slope of the tangent line? The tangent line is horizontal, right there, so the slope should be 0. And similarly, right there, the slope is also 0, okay? And let's look at the next one. Because there's no local minimum, we are not going to look at that, only look at the local maximum. And local maximum occurs right there, so the slope is also 0 again. And for graph C, let's look at the local minimum. And the slope of tangent, however, this time the derivative doesn't exist. Therefore, there's no slope. The slope doesn't exist. So in this case, this tangent line doesn't exist. However, we definitely see that the derivative doesn't exist because of the sharp corner, right? And the next graph, there's no local max, no local min. Let's skip that. For the function in the E, we can see that for the local maximum, the slopes of the tangent line, they're all zeros, right? And then for this local min, the slope of the tangent line doesn't exist. So the derivative doesn't exist at this point because of the sharp corner. And for the function in graph of F, the slope of tangent line at those sharp corners, they do not exist. Other than that, there's no other local max or local min. So we can see that the derivative doesn't exist at those local max and local min. So therefore, what's the slope of the tangent line at local max or local min? It's either 0 when they exist, right? Or when they do not exist, that of course just do not exist. Now actually this is a pretty important observation, and here comes the definition after that. Let f be defined as C if f prime of C is equal to 0, or f is not differentiable at x. We've seen those examples earlier in those graphs. Some are horizontal tangent lines, some are sharp corners, right? So therefore, when there's a horizontal tangent line, that's where the derivative is equal to 0. And sharp corner, that's where the f is not differentiable. Then this C, the value C, when this happens, either that or that, then C is called a critical number or a critical point of f. Both terms are used quite often, so please get familiar with both terms. In other words, if I look back to the graphs, just for instance, just look at the first one. C1 is called a critical number. C2 is called a critical number. Okay. Here in the second one, C is a critical number, and in the third one, C is a critical number, etc., and so on and so forth. Okay. Next theorem is the relative extreme occur only at critical numbers theorem. It's actually also called Fermat's theorem. It says if f has a relative minimum or relative maximum at x equals c, then c is a critical number or called critical point. In other words, f prime of c is either 0 or f prime of c fails to exist. So this is a pretty useful theorem because it gives us some direction on how to try to locate where the minimum or where the relative minimum or relative maximum occurs. Let's look at a couple statements. Can we say f prime, when f prime of c is equal to 0, then f has a relative minimum or maximum at c? So think about this question, and pause the video and then maybe refer back to problem 1 to see if that's true or false. In fact, this statement is false because, for instance, let's take a look at one of the graph here. We can see that at point t, x equals t, the tangent line is horizontal, which means the slope is 0, meaning the derivative at this point is equal to 0. However, it's neither a relative maximum nor a relative minimum. So therefore, this tells us the first statement is a false statement. So this is false. And the second statement says when f prime of c fails to exist, then f has a relative minimum or maximum at c. Well, think about this question again yourself, and this statement is actually false. I can give you one example like that. So if you graph a function and this function is like that, okay, like that, say this actually, if you use a graphing calculator and graph cube root of x, right there, maybe I should draw it better. This right there, there's a vertical tangent line right there, and therefore at this point the derivative doesn't exist. However, which means f prime of c fails to exist, and however it's neither relative minimum nor maximum right there. So therefore this statement is false. These two questions show you that the converse of this theorem is false. We can say f has a relative minimum or relative maximum at c, then c is a critical number or critical point. We cannot say if f prime at c is equal to 0 or fails to exist to conclude that one. So the backwards is not true. All right, after all this introduction, let's do some calculation. First, let's practice on locating the critical points or critical numbers for the following functions. So to find the critical point, and according to the definition, you look for the x values where the derivative is f prime is equal to 0 or doesn't exist. So we need to find f prime of x, which is 4x minus 4. And then we need to find x value so that the derivative is equal to 0, right? So therefore we set that to 0, and we can see that x is equal to 1. That's the only critical point or critical number that we have for this particular function. And actually, if you graph this guy, it should be something like that. It's a parabola, and then touching 1, and definitely that's the so-called critical point because it has horizontal tangent there. Second one, that's f prime of x equals 1 minus 1 over 2 square root of x. We have found the derivative of square root of x so many times, so hopefully you are comfortable with just writing it out immediately now. And if you need a little hint, you can think of square root of x as x to the 1/2, right? And then you find the derivative using the power rule. Now here we need to look for two things. One, where the x value so that this is equal to 0. Second, the x value so that the derivative doesn't exist. It's pretty easy to see that f prime of x fails to exist at x equals 0, right? Because this would not be defined in that case. So we found the first critical point. The second one, let's also set that to 0. Set this to 0. That means 1 minus 1 over 2 square root of x equals 0, and which means 1 over 2 square root of x is equal to 1, and then which means, so I'm going to say this means 2 square root of x equals 1 after we kind of cross multiply, meaning square root of x is equal to 1/2, or x is square both sides 1/4. So we do find two critical points or critical numbers for this function. Now next we're gonna actually find the extrema on a closed interval. So this lesson will focus on closed interval. In the future we'll talk about open interval. The guidelines for finding extrema on a closed interval is given below. To find the absolute max, absolute min of a continuous function f on a closed interval, so these steps only good for closed interval. Step 1, we find those critical numbers inside the interval AB. These are just candidates for the absolute max and absolute min. Second step, we are gonna evaluate f at those critical numbers and also the endpoints. So evaluate at critical numbers and at the endpoints. And then you just select the absolute max and the absolute min from the function values that we just we got from step B. Suggestion, always draw a graph to check your final answer. Now let's do the first one. So step 1, we have to figure out the critical numbers, right? So let's f prime of x is 4x cubed minus 6x squared. And this is a polynomial, so therefore there's no x value that the derivative fails to exist. We just need to set this to 0. And so which means let's factor this guy. So let's factor 2 out and then x squared as well. And then we have 2x minus 3 left. And therefore we found the critical number, set the we see x equals 0 from here. And for the second one, 2x minus 3 equals 0. That means x equals 3/2. So two critical values, 1 and 2. Next, we just need to evaluate the function value at the critical numbers and also at the endpoint, right? So now let's evaluate. So at the following, f of the endpoint, f of -3, and we also need to evaluate the f of 0 f of 3/2 and f of 3. So we just need to find those. So this is the endpoint, and this is the endpoint. And the middle, these two values, they are the critical points. F of -3, you might be able to just plug in your calculator and find those. So it turns out to be 81 minus 2 times -27, so which is 81 plus 54, which gives us 135. F of 0 is easy, which is just 0. F of 3/2 is 3/2 to the power 4 minus 2 times 3/2. And this is now equal to 81 over 16 minus 3, and which is equal to -1.69, okay, using your calculator. And f of 3 is 3 to the 4th minus 2 times 3 cubed. 81 minus the 54, which is equal to 27. And then you can see that this is definitely the absolute max, right? And this is the absolute min. So you can now conclude absolute max equals 135 at x equals -3 at the left endpoint, and absolute min is -1.69 at x equals 3/2. And lastly, I always encourage you to check on the graph of this function using a graphing facility. So it actually looks like something like this. Something like this. Actually, not that high. Just the right endpoint is just 27, right? So somewhere here. And you do see that, hey, the left endpoint, that's the absolute max. And here, this is absolute minimum. This is matching what we just found. Now, last example, we are going to look at this rational function here. This rational function, we look at this on this closed interval. We are going to find the absolute max and absolute min. And step 1, we have to find the derivative, right? So the derivative of f of x. And then here we will have to use the quotient rule. So the quotient rule in the denominator, it's the low function square of the low. And in the numerator, low d high, so the low function times the derivative of the high function, which is derivative of x, and which is 1, minus high function times derivative of this low function, right? Then we use the chain rule. It is 2 times x squared plus 1 times the derivative of the inner function, which is 2x. And by looking at the denominator, because of the square, the x is being squared, there's no way this will be 0. So therefore, there's no point in no x value in this interval, so that this is undefined. Therefore, we just need to set this to 0, basically set the numerator to 0 to find the critical points. So I'm going to set the numerator to 0. So this is actually 4x squared, right? 4x squared times x squared plus 1. And set this to 0. And I see a common factor here, x squared plus 1. So let's factor out x squared plus 1. And after that, we are left with x squared plus 1 from the first term, minus 4x squared equals 0. And this won't be equal to 0 because x squared can never be negative. And therefore, this has to be equal to 0. Let's simplify this a little bit. That means x squared minus 4x squared, which is negative 3x squared plus 1. This is equal to 0. Again, there's no way this can be 0, right? And solve this. This means x squared has to be equal to 1/3, or x equals plus or minus square root of 1/3, and which can be, you can rationalize it, plus or minus root 3 over 3. Now we've got two critical numbers inside this interval. Next, we just have to evaluate the function value at the endpoints and at the critical numbers, right? And a little observation here, this function is actually odd function, and then we can take advantage of this odd function, this property, so that f of negative x equals negative f of x, right? So save a little time, and we are gonna evaluate f of negative 2 first, which is negative 2 over square of the negative 2 plus 1, and then this whole thing square. This is equal to negative 2, and the bottom is negative 2 squared is 4, 4 plus 1 is 5, 5 squared, which is 25, so negative 2 over 25. And negative 2 over 25 is numerical, in decimal is negative 0.08. And now let's find f of negative square root of 3 over 3. By the way, I just mentioned that this function is odd. So therefore, after you find f of negative 2, you can quickly write f of 2 is actually the opposite value of this guy, which is 0.08. Again, because it's odd function. F of negative square root of 3 over 3 is equal to negative square root of 3 over 3 divided by, so let's do the square of this guy. So x squared, what is x squared? When you square that guy, actually it's 1/3, right? X squared is 1/3. So I'm going to say 1/3 plus 1, and then square of that. And then we have negative square root of 3 over 3. This is going to be 4 over 3, 4 over 3. And then when we square, it's going to be 16 over 9. And let's simplify it, which is equal to square root of 3 over 3 times the reciprocal of the 16 over 9, which is 9 over 16. Let's cancel the 3. So finally, we have negative 3 square root of 3 over 16. Now use your calculator. This is actually around negative 0.325-ish from my calculator, okay? And again, use the property that for the odd function, f of square root of 3 over 3 would be around 0.325. So with that, we can see this is the absolute maximum, and this is the absolute minimum. So therefore, we can now conclude that absolute max at x equals root 3 over 3, and f of root 3 over 3 is equal to 3 square root of 3 over 16, because it's going to be just opposite of this guy. And absolute min occurs at x equals negative square root of 3 over 3, and f of negative square root of 3 over 3 is negative 3 square root of 3 over 16. And at last, again, you should make a little graph using your graphing calculator, and take a look at from negative 2 to 2. This graph actually looks looks like something like this. Okay, it's symmetrical with respect to the origin, and you can verify that absolute max occurs at here and absolute min occurs at here, so that the graph matches what we just found.